This is a length of steel pipe with a piece of metal mesh inside it. There is nothing else. No piston, no crankshaft, no bearing, no seal, no moving component of any kind. You heat one end, and within about 30 seconds the tube begins to scream, loudly enough to be uncomfortable in a garage, and it will keep screaming for as long as you keep the heat on it. That sound is heat being converted directly into mechanical energy, and the machine doing it has no moving parts. Research versions of this device reach thermal efficiencies comparable to an internal combustion engine. They have flown on the space shuttle, and Los Alamos National Laboratory has spent decades on them. And here's the honest part, stated up front, because almost nobody covering this will say it plainly. The $50 version makes sound. Enormous, startling, genuinely impressive sound. Turning that sound into electricity you can use requires a second device that is neither cheap nor simple, and that is where every home build in this field runs into a wall. I am going to give you both halves, honestly. What you can absolutely build this weekend for the price of a pipe and a torch, and exactly what stands between that and a wire with current in it. Let me start with the physics, because this is one of the few genuinely surprising mechanisms left in engineering. Sound is not a substance traveling through air. Sound is a pressure wave, meaning a pattern of compression and expansion moving through a gas. And everything you have ever heard is air being squeezed and released a few hundred or a few thousand times a second. Now, think about what happens to a gas when you squeeze it. It heats up, release it, and it cools. That is the same principle behind a bicycle pump getting warm and behind every refrigerator on Earth, which means every sound wave is already a temperature wave. Every compression is slightly hotter, every rarefaction slightly cooler. And this is true of every sound that has ever existed. It is simply too small to notice. Thermoacoustics is the field that takes that relationship and runs it deliberately in both directions. Run it one way, and you push sound into a device and get cold out of it, which is a thermoacoustic refrigerator with no compressor. That direction deserves its own moment, because it is the one that has actually reached the public. If you drive a stack with a loudspeaker, instead of heating it, the same mechanism runs backwards. The oscillating gas parcels pick up heat at one end of the stack and deposit it at the other, pumping heat against the temperature gradient exactly as a refrigerator does. The result is a cooling machine, whose only moving part is a speaker cone, and whose working fluid is an inert gas rather than a chemical refrigerant. That matters more than it sounds, since the entire refrigeration industry spent the 20th century cycling through refrigerants that turned out to be toxic, then flammable, then destructive to the ozone layer, then powerful greenhouse gases. A machine that works on helium or plain air sidesteps that entire history. Working thermoacoustic freezers have been built and demonstrated publicly, including a well-known ice cream cabinet developed with university researchers as a proof of concept, and the technology has been flown in space, so the same physics, run in either direction, gives you an engine with no moving parts or a refrigerator with almost none. Very few mechanisms in engineering are that symmetrical. Run it the other way, and you put heat in and get sound out, which is a thermoacoustic engine, and that is what we are building. Here is what actually happens inside the tube. You have a resonator, which is simply a pipe of a length that likes to ring at a particular note exactly like an organ pipe. Inside it, you place a stack, meaning a porous material with a great deal of surface area, often metal mesh or a honeycomb of thin plates. Then you create a temperature difference across that stack, hot at one end and cool at the other. Now follow a single parcel of gas sitting inside the stack. The gas is not still, since it is oscillating back and forth with any tiny sound already present in the tube, and there is always some. As that parcel moves toward the hot end, it picks up heat from the stack surface, which makes it expand. That expansion pushes the gas around it, which strengthens the sound wave. As it swings back toward the cool end, it gives that heat up to the stack, which makes it contract, and the timing of that contraction also reinforces the wave. So the parcel absorbs heat at one point in the cycle and rejects it at another. And the difference comes out as mechanical work in the form of a louder sound wave that is a thermodynamic cycle, and it is being performed by the gas itself rather than by a piston. Multiply that by every parcel in the stack, and once the temperature difference passes a critical threshold, the tube spontaneously bursts into sound and sustains it, converting your heat into acoustic power continuously. There is no cleverness in the hardware. The gas is doing all the work. So the obvious question is how long people have known about this, and the answer is longer than almost anything else in this series. In 1777, an English scientist named Byron Higgins reported that a hydrogen flame placed inside a tube would produce a musical tone. It became known as the singing flame, and for decades it was treated as a parlor curiosity with no explanation. Around 1850, glassblowers reported something similar, and a physicist named Sondhaus studied it. When a glassblower blew a hot bulb at the end of a narrow tube, the tube emitted a clear tone as it cooled, and the pitch depended on the dimensions. Then, in 1859, a Dutch physicist named Peter Ricci did the experiment that turned it into a repeatable demonstration. He placed a heated wire gauze inside a vertical open tube, at roughly a quarter of the way up from the bottom, and the tube produced a loud, sustained tone. That arrangement is now called a Ricci tube, and it is the single most reliable way to see this effect with your own eyes. It is also, and this matters for our purposes, the cheapest. For over a century after that, none of it had a proper theory. It was a demonstration that physics teachers used, and nobody could fully explain. That changed in the 1970s, when a Swiss physicist named Nikolaus Roth developed the mathematical framework that finally described what the gas was doing and turned a curiosity into an engineering discipline. And then it became serious, at a place that takes physics extremely seriously. At Los Alamos National Laboratory, researchers, including John Wheatley and Greg Swift, built thermoacoustics into a genuine field through the 1980s and 1990s. They were not chasing a novelty. They were chasing an engine with no moving parts, because in certain applications, that property is worth more than efficiency. It is worth being precise about why, since most people underwrite it. Almost everything that fails in a machine fails at a moving interface. Bearings where seals harden and leak. Pistons scuff their cylinders. Valves stick. Lubricant degrades and has to be replaced on a schedule, and every one of those is a maintenance visit or a breakdown. Remove all of them, and the failure modes that remain are corrosion and material fatigue, which are measured in decades rather than in service intervals. For a device on a spacecraft at the bottom of a borehole, inside a sealed industrial process, or in a village 3 days from the nearest technician, that changes the entire calculation. A machine that is 20% efficient and never needs touching can be worth far more than one that is 40% efficient and needs a service every year. That is the argument this technology has always rested on, and it is the reason serious institutions keep funding it while it remains completely unknown to the public. Their landmark result came in 1999 when Scott Backhouse and Greg Swift published a Thermoacoustic Stirling heat engine in Nature, reaching roughly 30% thermal efficiency. The reason that particular design achieved so much more than earlier ones comes down to a distinction worth understanding, since it separates the toy from the engine. The simple version, and the one you will build, is a standing wave device. The sound bounces back and forth in the tube and forms a stationary pattern, and the gas parcels in the stack move slightly out of step with the pressure changes. That imperfect timing is deliberate, and it is also the problem, since a portion of the heat transfer happens at the wrong moment in the cycle and is simply wasted. Standing wave engines are inherently limited by this, which is why they top out at modest efficiency no matter how well built. The advanced version is a traveling wave device built in a loop rather than a straight tube, so the sound wave circulates around the circuit rather than reflecting back on itself. In that geometry, the pressure and the motion of the gas can be brought into proper phase with each other, and the gas parcels execute something extremely close to an ideal Stirling cycle. That is why Backhouse and Swift called their machine a thermoacoustic Stirling engine, and it is why the efficiency jumped into engine territory. The lesson for a builder is simple. A straight tube demonstrates the effect beautifully and cheaply. A loop is where the real performance lives, and it is a considerably harder build. Sit with that number, because it is the one that changes how you see this. 30% is in the same territory as a petrol engine, and it is being achieved by a device with no pistons, no crankshaft, no valves, and no seals. Now the deployment, and it is worth seeing at 4 separate scales. Start with space, which is where no moving parts is worth almost any price. On a spacecraft, every mechanical component is a potential failure you cannot repair. A device that runs for years with nothing rubbing against anything else is enormously attractive. And a thermoacoustic refrigerator was flown and operated on Space Shuttle mission STS-242 in 1992 research. Programs have continued on thermoacoustic converters for space power, driven by exactly that reliability argument. Then the laboratory and industrial scale, where thermoacoustic devices are used for cryogenic cooling, meaning producing extremely low temperatures for liquefying gases and cooling sensitive instruments. In that world, a cooler with no moving parts near the cold end is genuinely valuable, since vibration ruins measurements. Then the humanitarian scale, which is the most interesting of the four. A project called SCORE set out to solve two problems at once. For households without electricity, those households cook over fire every day, and that fire produces far more heat than the cooking requires, with the surplus going straight up into the air. So the project developed a cooking stove with a thermoacoustic engine built into it, using the waste heat from cooking to produce sound, and converting that sound into a small amount of electricity for lighting and phone charging. One fire, cooking, heating, and power, and nothing inside it to wear out or be serviced by someone who will never visit. That is the clearest statement of what this technology is genuinely for. And the problem it addresses is enormous. Very large numbers of households worldwide cook over open fire or basic stoves and have no reliable electricity, which means no light after dark beyond kerosene, no phone charging without walking to a shop, and children studying by flame. Solar handles some of that, and a thermoacoustic stove attacks it from a completely different angle. Since the fire is being lit anyway, every single evening, regardless of whether the sun came out, the engineering constraint that shaped the design is the one worth noting. It had to be manufacturable and repairable locally, which rules out anything with precision bearings or sealed mechanisms. And a device whose only critical parts are a tube, a stack, and a metal diaphragm fits that requirement better than almost any alternative. Whether it ever reaches scale is a separate question. And the honest answer is that these projects are difficult, and many do not. But the reasoning behind it is the cleanest demonstration of why an engine with no moving parts is worth pursuing even at modest efficiency. And then the waste heat scale, which is where the commercial interest sits. Enormous quantities of industrial heat are rejected at temperatures too low to be worth running a conventional turbine on. A device that turns that heat into power with no moving parts, and therefore no maintenance schedule, is a genuinely attractive proposition. And several research groups have pursued exactly that. This channel exists for exactly this kind of straight answer. One honest method a week, and subscribing is how those keep arriving. Now the catch, and here is where I have to be completely straight with you. Everything I have described produces acoustic power, meaning sound, that is real mechanical energy, and it is genuinely being converted from heat. But you cannot plug a lamp into a sound wave. To get electricity, you need a linear alternator, which is a device with a magnet on a spring inside a coil, positioned so that the sound wave drives the magnet back and forth and induces current in the coil. And that is where every home project in this field stops, for three reasons. The first is that a linear alternator is a precision component. It has to be tuned so its natural resonant frequency matches the frequency of your engine, or almost nothing transfers. Get that matching wrong, and you have a loud tube and a warm coil. The second is that it reintroduces a moving part, which is somewhat the point of the whole exercise, although a magnet on a spring is far more reliable than a piston in a cylinder. The third is cost. Purpose-built linear alternators are not a hardware store item, and the research devices use custom units, so the honest split is this. The heat-to-sound half of thermoacoustics is cheap, dramatic, and buildable in an afternoon. The sound-to-electricity half is a serious engineering project, and anyone showing you a $50 tube charging a phone is not showing you the whole system. Now the arithmetic, so you know what the real numbers look like. Research thermoacoustic Stirling engines reach around 30% in converting heat to acoustic power, which, as I said, is genuinely impressive. Put a linear alternator on the end, and you lose a meaningful share, converting that sound to electricity. So overall, heat to electricity figures in good research devices land somewhere in the region of 15 to 25%. That is respectable, and it is achieved with helium at high pressure inside precisely engineered geometry, which is what a national laboratory can build and a garage cannot. A home-built standing wave engine running on air at atmospheric pressure with a rough stack, operates far below that. Expect single-digit percentages at best in acoustic conversion, and watts rather than kilowatts even if you solve the alternator problem. So the realistic target for a home build is a demonstration that genuinely works, a small amount of usable power if you push it, and a genuinely deep understanding of a mechanism almost nobody has heard of, that is worth $50. Powering a house is not on the table. Now let me show you how to build the part that does work. The resonator is a tube. A steel or aluminum pipe, roughly 1.5 inches to 3 inches in diameter and a couple of feet long, is a good starting point, and it costs $10 to $25. A cardboard tube works for a first attempt, though it will not survive much heat. Length sets your pitch, exactly like an organ pipe, and a longer tube gives a lower note. The stack is your critical component. For the classic Reiki tube, it is simply a disc of metal gauze or a wad of fine steel wool fitted snugly across the inside of the pipe. $5 of stainless mesh is plenty. Position matters enormously, and this is the detail people get wrong. For a Reiki tube open at both ends, the gauze wants to sit roughly 1/4 of the way up from the bottom. Too high or too low and the tube stays silent, and moving it a couple of inches is the difference between nothing and a sound that makes people jump. The heat source is your remaining cost. A propane torch, $15 to $25, is the simplest way to heat the gauze. A coil of nichrome wire fed from a low voltage supply is the more controllable option and lets you run continuously. The method is straightforward. Stand the tube vertically, heat the gauze thoroughly until it is glowing, then remove the flame. That last instruction is the one that surprises everyone. The Reiki tube typically does not sing while the flame is in it because the flame disrupts the airflow. Take the heat away and the tube starts to roar, and it will continue until the gauze cools. Total cost lands somewhere around $30 to $60, depending on what you already own, which is where the figure in the title comes from. If it does not sing, and a good number of first attempts do not, the cause is almost always one of 4 things. The gauze is in the wrong place. This is by far the most common problem, and the fix is to move it. Fit it so you can slide it, try it at 1/4 of the way up, then try 1 inch either side. There is a genuine sweet spot, and it is narrower than people expect. The gauze is not hot enough. It needs to be properly glowing rather than merely warm, since the effect only begins once the temperature gradient crosses a threshold. Heat it longer. The gauze is too dense or too sparse. You want plenty of surface area with the air still able to flow through freely. A tightly packed wad blocks the tube, and a thin single layer has too little surface to exchange heat, or the tube is not vertical. The Reiki design depends on hot air rising through the gauze to establish the flow, so lay it on its side and it will fall silent immediately. That one catches almost everybody, and it is also a neat way to demonstrate that the convective flow is genuinely part of the mechanism. Work through those 4, and the tube will sing. If you want to go further into a genuine engine rather than a demonstration, the next step is a closed resonator with a proper stack of parallel plates, hot and cold heat exchangers at either end of it, and eventually a loop geometry for the traveling wave design that Los Alamos used. Each of those steps is a real project, and the physics rewards precision at every one. Now the section the sponsored videos skip, because this has real limits. The first is the noise, and I want to be clear that this is not a metaphor. A working thermoacoustic engine is loud, and a well-tuned one is painfully loud. Research devices are enclosed for exactly this reason, and any practical machine has to deal with the fact that its working fluid is a sound wave you can hear from the next room. The second is that atmospheric air is a poor working gas. Serious devices use pressurized helium because it carries acoustic power far better, and that is a large part of why laboratory efficiencies are unreachable at home. The third is the alternator problem I have already described, which is the genuine barrier between a demonstration and a generator. The fourth is that these engines want a substantial temperature difference to start at all. Below the critical gradient, nothing happens whatsoever, and the tube simply sits there. The fifth is heat exchanger design, which is the unglamorous part that determines everything. Getting heat into and out of the gas efficiently is where most of the real engineering effort in this field goes. And the sixth is that for producing electricity at home, A thermoelectric module or a small engine is simpler, cheaper, and more effective. This wins on reliability and on having no moving parts and on essentially nothing else at household scale. Now the safety section. You are working with an open flame and metal heated to glowing, so the ordinary rules apply. Work on a non-flammable surface, keep the area clear, and never leave a torch unattended. The tube gets extremely hot and stays hot long after it stops singing, so treat every part of it as dangerous to touch until proven otherwise. The noise is a genuine hazard rather than a nuisance. A well-tuned Reiki tube can exceed the level at which hearing damage becomes a real concern, so wear hearing protection and do not run it for extended periods indoors. Ventilate since you are burning fuel in the room, and a propane torch consumes oxygen and produces combustion products, and do not pressurize a home-built resonator. Research devices run pressurized helium in vessels engineered for it, and a sealed pipe under pressure with a flame on it is not a project, it is an accident. The ledger for the whole story then: a steel pipe, $10 to $25. Stainless mesh or steel wool for the stack, about $5. A propane torch, $15 to $25, or a nichrome wire, and a supply for a controllable version. Hearing protection, $10. Total, $30 to $60 for a device that converts heat directly into mechanical energy with nothing moving inside it. Here's the thing worth keeping from all of it. In 1777, somebody noticed that a flame in a tube made a musical note, and for nearly 200 years that observation sat in physics demonstrations as a curiosity with no purpose. Nobody could explain it properly until the 1970s. Then, a national laboratory looked at the same effect and built an engine reaching 30% efficiency with no moving parts, and a version of it flew in space. The gap between those two sentences is the interesting part. The physics did not change. What changed is that somebody finally asked what the singing flame was actually doing, and found a thermodynamic cycle hiding inside a party trick, which is worth remembering the next time something in your life makes an unexplained noise. Sound is pressure, pressure is temperature, and a machine that understands that relationship well enough can run on nothing but a difference in heat. You have probably already heard a weak version of it without knowing. A kettle that whistles oddly as it heats. A wood stove flue that hums at a particular point in the burn. A hot glass tube that rings as it cools. Those are all the same effect, arriving uninvited in ordinary objects that happen to have a temperature gradient across a narrow passage. Once you know what the mechanism is, you start hearing it everywhere, and it stops being a strange noise and becomes a small demonstration of thermodynamics running in your own house. Everything this channel has gathered on turning heat into useful work, the engines, the chillers, the trickle sources, each with its real numbers and real limits, lives in one place, linked right below. And the comments are where this one earns its keep. Has anyone here actually built a Reiki tube? And how loud was yours? Tell me your pipe length and where you put the gauze, because that placement is the whole trick, and almost nobody publishes what worked. As for the machine that runs an air conditioner on heat alone, with no compressor anywhere in it, patented by Albert Einstein in 1930, that is on screen right now. Different cycle, same idea. Till next time.